Welcome to our paper, Geometric-Photometric Event-Based 3D Gaussian Ray Tracing. In this work, we propose a new framework for event-based 3D Gaussian reconstruction to address the temporal window size trade-off. We introduce an efficient event-by-event ray tracing framework that connects event-by-event depth estimation with 3D GS optimization. Our method achieves state-of-the-art results on real-world datasets and competitive results on simulation datasets without relying on any prior knowledge. It also achieves the fastest training time among the evaluated state-of-the-art methods. Prior works generally employ one of the following two strategies. The first strategy is event-by-event rendering. This approach can leverage the dense temporal information of events, but suffers from noisy outputs due to per-pixel processing, as well as slow training. The second strategy is to render two frames. This approach can leverage the dense spatial information of a scene, but suffers from the temporal window size trade-off. Long temporal windows produce blur, while short windows lack sufficient cues for optimization. So our key idea is shown here. We render the intensity image only once, without sacrificing the fine-grained temporal resolution of the event stream. And we use IWE to connect temporally dense events and a spatially dense intensity image. The architecture is shown here. We decompose the rendering and loss computation pipeline into two branches, a temporally dense geometric branch and a spatially dense photometric branch, because structure comes from motion while appearance emerges instantaneously. The geometric branch leverages the dense temporal information of events to optimize the scene structure from motion. In the geometric branch, we render event-by-event depth using a Gaussian ray tracing renderer. Then, event-by-event flow is analytically computed from the event-by-event depth and camera parameters. Since the flow of each event is known, a blur-free motion compensated image, called an IWE, can be generated by warping all event coordinates to a reference timestamp. We then introduce a contrast loss, a sharpness-based loss function applied to the generated IWE. As the IWE becomes sharper, the loss value decreases. Therefore, minimizing the contrast loss encourages the event-by-event flow and event-by-event depth to become more accurate, which in turn leads to a more accurate reconstruction of the scene geometry. On the other hand, the photometric branch optimizes the appearance by leveraging the dense spatial information represented by the 3D Gaussians. In the photometric branch, an intensity image and depth map are obtained through snapshot-based rendering. Next, by computing the intensity gradient and optical flow from the rendered intensity image and depth map respectively, and then taking their dot product, we can approximate the instantaneous brightness change. By computing the L2 and SSIM loss between the instantaneous brightness change and the IWE, we can update the scene appearance so that it becomes consistent with the observed events. With these mechanisms, our method can reconstruct 3D Gaussians from real-world event streams with reduced noise and blur. In this comparison, robust eNerf adopts an event-by-event strategy, whereas IncEvent-EGS adopts a two-frame rendering strategy. Our method also achieves competitive results on simulated color event datasets. Finally, we present some additional visualizations. Thank you for watching. Code is available on GitHub. For more details, please check our paper.